A fish declared extinct for 65 million years came up alive in a trawl net on the 22nd of December 1938. Early morning at East London Harbour, South Africa, the Nirine had just docked. Captain Hendrik Goosen had pulled his nets from the Chalumnae River mouth, where brown river water bleeds into the Indian Ocean, and the catch lay wet and salt-smelling across the deck. Marjorie Courtenay-Latimer was 26 years old. She ran the East London Museum. She had a standing arrangement with Goosen. Call her when something strange comes up. That morning, he called. She moved through the pile of sharks and rays. Then she stopped. Beneath them, half buried, was something blue, iridescent, wrong. She wrote later, in her own words, "I picked away at the layers of slime to reveal the most beautiful fish I had ever seen. It was 5 feet long, a pale mauvey blue with faint flecks of whitish spots. It had 4 limb-like fins and a strange puppy dog tail. 4 limb-like fins. Not rays, not spines, lobed, fleshy, arranged in diagonal pairs like something that had once considered walking. No modern fish has fins like that." Courtenay-Latimer sketched it by hand and sent the drawing by telegram to J.L.B. Smith at Rhodes University. Smith was one of South Africa's foremost ichthyologists. When the sketch arrived, he later wrote that a bomb seemed to burst in his brain because he recognized what he was looking at. Not a new species, an old one, impossibly catastrophically old. Smith would not see the preserved specimen himself until the 16th of February 1939. What he confirmed that morning put every biology textbook in the world quietly out of date. But the rediscovery was only the beginning. Decades later, a genome sequencing paper would be filed, and what it found inside this animal's DNA will reframe not just the coelacanth, but the evolutionary tree every textbook has printed for the last 100 years. That paper is where this record ends. The consensus settled fast, too fast. By 1939, the scientific world had a clean story. The coelacanth was a living fossil, a creature frozen in time. It had survived in deep water by changing nothing, hiding in the dark, waiting out the extinction event that erased its relatives. Case closed. The answer satisfied everyone. It was also incomplete. For decades, that framing held. The coelacanth became a symbol of biological stillness, a creature that evolution had simply skipped. Hans Fricke's submersible team confirmed in January 1987 that living specimens off the Comoros Islands moved slowly, hovered near cave entrances, conserved energy. Nothing about them seemed urgent. Nothing seemed new. The living fossil story felt confirmed. Then, in 2013, Chris Amamiya and colleagues at the Broad Institute sequenced the coelacanth genome. The genome did not cooperate. What Amamiya's team found, published in Nature, was not a frozen record. The coelacanth carried active immune genes, not dormant, not vestigial, active. It carried functional olfactory receptors, tuned specifically for detecting chemical compounds associated with land environments. A deep water animal, living at 150 meters, with a nose calibrated for a world it never visits. That is strange. This is stranger. Buried in the coelacanth genome were Hox gene clusters, the same regulatory sequences that direct limb development in tetrapods, in humans, in every 4-limbed vertebrate that ever crawled out of the sea. These are not fossil sequences. They are functional architecture. The genome carried instructions for building limbs in an animal that does not build limbs. A frozen creature does not maintain active chemistry for environments it abandoned. A frozen creature does not keep the blueprint for a body plan it never uses. So the living fossil story had a hole in it, a specific molecular hole written in base pairs and published in a peer-reviewed journal in 2013. The question that remained, if this genome is still carrying those instructions, what exactly is it waiting for? Here is what the genome said. In 2013, Chris Amamiya at the University of Washington and a team of 31 researchers sequenced the complete coelacanth genome and published the results in Nature. The paper ran to 9 pages. The finding buried in page 4 stopped evolutionary biologists cold. The coelacanth's protein-coding genes evolve at 8 times the rate of a shark's, slower. 8 times slower, the slowest molecular evolution ever recorded in a vertebrate. The animal alive in the Indian Ocean today is, at the genetic level, nearly identical to the creature swimming 400 million years ago. Not similar, nearly identical. But nobody in 1939 could have predicted what came next. The same 2013 paper, confirmed by follow-up analyses in 2019, found that the coelacanth is more closely related to lungfish and tetrapods, 4-limbed land animals, than to any ray-finned fish. A tuna is further from a coelacanth than you are. Read that again. You share more molecular ancestry with this fish than a tuna does. The genome also contained functional regulatory sequences, enhancers, that activated limb development gene expression when Amamiya's team inserted them into mouse embryos in a laboratory setting. A 400-million-year-old fish carrying the molecular instructions that helped build your arms, a working blueprint never deployed. Marjorie Courtenay-Latimer sketched that fish on the 22nd of December 1938. Pencil on paper, 4-lobed fins, careful handwriting in the corner. She did not know she was drawing the document that would eventually prove every vertebrate on land descended from something that looked exactly like what she pulled from that net. The sketch was not a record of the past. It was a diagram of the present, still operational, still running unchanged in the dark water off the Comoros. What the index concludes: the coelacanth is not a survivor of extinction but proof that evolution does not always move forward, and that the bridge between sea and land never fully closed,